This video is about the second translation theorem, also known as the second shifting theorem. In order to discuss that, to get ready to discuss that, we're going to define the Heaviside function. We're going to talk about what it does to a function when we multiply it by a Heaviside function. Then we're going to talk about how to write a piecewise function in terms of the Heaviside function. And then we'll finally state the second translation theorem and derive it. And then once we have that theorem, which involves which will explain how to compute the Laplace transform of a function of t times a Heaviside function, we'll actually practice applying it. So we will compute the Laplace transform of something that looks like this, and then we will compute the inverse Laplace transform of something that looks like that. So let's start with the Heaviside function. Now, the Heaviside function can be defined on any interval, including the entire real line. But in this class, we'll tend to define it on the interval from 0 to infinity because we are talking about functions defined on the interval from 0 to infinity when we're using the Laplace transformation. So for our purposes, the Heaviside function of t minus a is equal to this. It's 0 until t equals a, and then at t equals a, it's 1. Now this notation is a little bit different. Students are not typically accustomed to this notation. Like if you have t equals 3, you don't really want to substitute in 3 to this. You want to think of this notation as representing this situation. So assuming that a is greater than 0, here's a, and the Heaviside function is equal to 0 until you get to a, and then at t equals a, it jumps up to 1. So the Heaviside function at t minus 3 is 0 until you get to 3, and then it's equal to 1. The Heaviside function at t minus 5 is 0 until you get to 5, and then you go up to 1, and so on. That's how you want to think of it. We're going to multiply other functions by this. You can think of this as an on-off switch. If I multiply a function by this, it's basically turning that function off until we get to t equals a. And then at t equals a, we multiply by 1, and it turns that function on. So let's say you've got a function f of t, and f of t looks like this. So maybe that's our f of t. Well, if I multiply that by t minus, or h of t minus a, what that does is it turns it off until we get to a, and then at a, it turns it on. So we would jump up and get the rest of this function. So the Heaviside function is 0 until we get to a, and then it would just give us that function. So you can think of this as your on-off switch. And if you're saying, why on earth would I have an on-off switch? Remember, differential equations are often mathematical models. If you're talking about adding up forces, if you're looking at a sum of forces problem, the functions on the right-hand side of that differential equation, those non-homogeneous terms, are typically called forcing terms or forcing functions. It's some extra force typically that's added to the system. You might want to turn those functions on and off. You might want to say, we're not doing anything until t equals 5, and then I'm going to flip a switch, and then I'm going to turn this function on. So it makes sense that we would want to have a function that behaves like an on-off switch, because sometimes when you're talking about some physical system, you are literally flipping a switch and turning things on and off. And anytime you have a piecewise function, something that looks like this, you might want to represent that in terms of the Heaviside function as well. These can be the forcing functions on the right-hand side of that differential equation. And again, I'm thinking of the right-hand side as representing all of those non-homogeneous terms in the differential equation. Okay, so if I take a function and I multiply it by h of t minus a, it turns it off until t equals a, and then it turns it on at t equals a. Now, if you are saying to yourself, but what if I don't want to start here and go on. I want to start there and go on. I just want to delay the whole thing a little bit. I want to delay it, by a seconds or a minutes or by a units of time, whatever a happens to be. So you just want to turn this function on, but you want to wait until t equals a to turn it on. So it would have like this shape. I'm going to try to draw it the same way. Maybe successfully, maybe not successfully. Now, maybe that function actually would appear over here. If I were to looking at it as a function of t, maybe it's defined from negative infinity to infinity, but we're just considering that part that starts at t equals 0. Well, then I don't want that part over here that's on. Like I'm not interested in that part when I shift the whole thing to the right. So if I want to take this function and turn it on, from its starting point at t equals a, so I'm just delaying it a seconds or a units of time. In that case, actually let me use a different color for that. I'm going to take f and evaluate it at t minus a. That shifts the graph of f t units or a units to the right. And then I want to multiply that by h of t minus a, so that I'm guaranteed that it's 0 until we get to a. And then at t equals a, it turns on and it gives me this graph right here. And that was supposed to be identical to that graph over there, even though I didn't do a very good job. So this is sort of turning that function on at t equals a. It's sort of a delayed onset. Okay. So now we see that this is another way of delaying turning on that function. It turns out that by thinking of this as an on-off switch, we can take any piecewise function, not just piecewise functions that look like this or this, and represent them in terms of the Heaviside function. And that's going to be really beneficial for us because we know the Laplace transform of a function times a Heaviside function, as we'll see in our second translation theorem. Let's talk about how to write a piecewise function. In terms of the Heaviside function. Now, when I heard the name Heaviside function, I thought someone was sort of using their imagination and saying this is a Heaviside function because it had like a heavy side. Like it literally had like one side was heavier than the other. Like this is light and it's sort of floating, and then this one is heavy and it's not. That's what I was thinking. It's actually a guy's name. There's a guy named Heaviside, and he is the person who came up with this. Because we go from 0 and then we jump up to 1, sometimes this is called the unit step function. I still think of it as a Heaviside function with a heavy side, but it's actually not because it has a heavy side. It's because there's a guy named Heaviside who came up with this. Okay. So sometimes instead of using this h of t minus a notation, which I think is pretty standard, it's also written like this. This is the notation that ZIL uses. I know we're not using the ZIL book this semester, but we are using their table of Laplace transforms. So this u of t minus a is the unit step function at t minus a. It's the same as the Heaviside function. It's 0 until you get to a, and then it jumps up to 1. Okay. So if I want to write a piecewise function in terms of the Heaviside function, this is the way I do it. Let's say I've got a piecewise function f of t, and excuse me, for t between 0 and a, f of t is equal to g of t, and for t between a and infinity, f is equal to h of t. Well, the way I do that is I think of this as an on-off switch again. I'm assuming that g is actually on at t equals 0. So I just write this down. And then I want to turn it off at t equals a. So I will subtract g of t and I will multiply by h of t minus a. Now the fact that we're turning it off is explained by this negative sign. So I'm subtracting this function as soon as t is equal to a. Because remember, the Heaviside function is equal to 0 until you get to a, and then it's equal to 1. So for t between a, or 0 and a, we're going to get 0. So we'll have g of t minus 0 in that case. For t between 0 and a, we just get g of t. Now for t greater than a, then this Heaviside function is equal to 1. So what I would have there is g of t minus g of t times 1. So I've turned this on, and then at t equals a, I'm turning this off. I have g of t minus g of t, and that gets me 0. But that's not what we have here. It's not just g of t on the interval from 0 to a and then 0 otherwise. At t equals a, we turn the h of t function on. So we would add h of t times h of t minus a to turn this function on. Now, most students require a little bit of practice with this, but once you practice, it's really not too bad at all. So let's practice a little bit. Let's say our f of t is equal to 2t on the interval from 0 to 1, and it's equal to sine of t on the interval from 1 to infinity. Oops. Okay, so in this case, the function that is initially on is 2t. The one that is on at t equals 0, you just write it. It doesn't need a Heaviside function. And if you're turning it off at t equals 1, you're going to subtract that function multiplied by h of t minus 1. And again, in practice, if this is 1 on the interval from 1 to infinity and 0 on the interval from 0 to 1, when t is between 0 and 1, we get 2t minus 2t times 0. So we just get 2t. Then when t is greater than 1, this is 2t minus 2t times 1. So 2t minus 2t is going to be 0. So we've turned this off. Now that doesn't account for the sine of t. I want to turn on the sine of t at t equals 1. So I will add sine of t times h of t minus 1. Whoops, running out of space there. This is turning on the sine of t function at t equals 1. Again, it's like flipping a switch and then changing that force that's acting on the system. Let's do one more of those. So let's say our f of t is this. It's 3 on the interval from 0 to 2, and it's 2 minus, or t minus 4. Let's say t squared on the interval from 2 to 7, and then let's say cosine of t for the interval from 7 to infinity. And we'll include the lower limits there. Okay, so this has 3 pieces. So 3 is initially on, and then then at t equals 2, I'm turning this off. So I subtract 3, and I multiply by the Heaviside function at t minus 2. Okay, and then I want to turn this function on at t equals 2. So I just take the function, t minus 4t squared. And since I'm turning it on, I multiply by h of t minus 2 there. So I'm adding it, and I'm multiplying by the Heaviside function at the time that I want to turn it on. So this is turning on t minus 4t squared at t equals 2. And then at t equals 7, I want to turn it off. So I'm subtracting that same function, and I multiply by h of t minus 7. And then at t equals 7, I want to turn the cosine function on. So I'm adding the cosine function at h of t minus 7. Now, if you're saying to yourself, are you sure that's what that's equal to? Let's check it out. We can always go backwards. If I have something that looks like this, and it would probably have been simplified a bit. Let's say somebody simplifies it. I've got a Heaviside function at t minus 2 here and another one here. So this would be 3 plus t minus 4t squared minus 3 times the Heaviside function at t minus 2. And then we'll have a positive cosine of t minus t minus a negative 4t squared, so that's plus 4t squared times the Heaviside function at t minus 7. So let's say you solve a differential equation and you end up with this as your y of t. And you want to write it as a piecewise function so that everybody has a better understanding of what that function is. Well, then I would write it this way. Since I have a Heaviside function at t minus 2 and one at t minus 7, I know I have 3 intervals. The first interval is from 0 to 2. The next one is from 2 to 7. And then the last one is from 7 to infinity. So you can just write it like that, or you can write it like that if you want to. Now remember, the Heaviside function at t minus 2 looks like this. It's 0 until you get to 2, and then at 2 it jumps up to 1. And then the Heaviside function at t minus 7 looks very similar, but it's 0 until we get to 7. This is not to scale. And then at 7, it jumps up to 1. Okay, so let's see if this is giving us what we want it to give us. So between 0 and 2, this Heaviside function is off and this Heaviside function is off. So both Heaviside functions are 0 on that interval. So between 0 and 2, we get 3 plus something times 0 plus something else times 0. So 3 plus 0 is just 3. Is that what it's supposed to be? It is. Okay, great. And then between 2 and 7, this Heaviside function is on. So this function is 1, but this function is off. This function is 0. So between 2 and 7, we get 3 plus this expression times 1. So that's t minus 4t squared minus 3 times 1. Plus this times 0, because the Heaviside function at t minus 7 is going to be 0 on the interval from 2 to 7. And if you simplify that, you see that the 3's reduce, and you just get that. Nice. And then on the interval from 7 to infinity, this guy is 1 and this guy is 1, so we end up with this, because I've got this plus this times 1 plus this times 1. So I have 3 plus t minus 4t squared minus 3 plus cosine of t minus t plus 4t squared. Because we were turning things on and off, you see the same terms, but they reduce. You have the 3 and the minus 3, and then you have the t and the minus t, and the negative 4t squared and the positive 4t squared. And so we end up with 3 on the interval from 0 to 2, t minus 4t squared on the interval from 2 to 7, and cosine of t from 7 to infinity, which is exactly what we started with. Okay, so that is how we write functions in terms of the Heaviside function. And the reason we want to do that is because of the second translation theorem. So let's go to the second translation theorem now. I'm going a little bit faster because my battery is dying and I actually left my cord at home. So I'm hoping to finish this video before the battery dies. We'll see. The theorem says if f has a Laplace transform, f of s for s greater than a greater than or equal to 0, then the Laplace transform of f of t minus a times h of t minus a is equal to e to the negative as times f of s. And this is for s greater than a. Isn't that nice? Now, in practice, what this says is it says you have to identify a from this, and then you know you're going to have an e to the negative as in your Laplace transform. And then you also have to identify f. So this is e to the negative as times the Laplace transform of f of t. So we'll have f of t minus a here. We need to identify f of t from that. And once we have f of t, we'll take its Laplace transform, and that's our f of s. So that's what we're doing in practice. Let me show you where that comes from. Just use the formal definition of the Laplace transform. So if I want the Laplace transform of f of t minus a times h of t minus a, I can use the definition. It's e to the negative st times f of t minus a times h of t minus a. We're integrating with respect to t. But remember, h of t minus a is 0 until we get to a. And then it jumps up and it gives us a 1. So what that means is that this integral from 0 to infinity can be split up into two integrals. It's the integral from 0 to a times e to the negative st, and then we have f of t minus a times 0, plus the integral from a to infinity of e to the negative st times f of t minus a times 1 with respect to t. And of course, the area under the curve, where the curve is given by 0, is just 0, and that's this. Now that looks a lot like the Laplace transform, but notice the typical definition of the Laplace transform starts at 0, and this one starts at a, and this one doesn't have an f of t, it has an f of t minus a in it. Well, if I use a substitution, let's just let u equal t minus a, then du is just 1 dt, and t can be written as u plus a. If I just solve that equation for t, then this integral can be written in terms of u in this way. I have e to the negative s times t, where t is replaced by u plus a. And this is f of u by definition. Du and dt are the same thing. And then when t equals a, u will equal 0. And as t goes to infinity, if a is a constant, u will also go to infinity. Oops. And so we have this. But remember, this variable of integration is a u. A and s are just constants. So we could factor out the e to the negative as there. Let me write it this way. And I think this is going to be the end of the video because my battery is definitely about to die. Okay. So just using exponent properties, this is e to the negative s times u times e to the negative s times a times f of u du. We're integrating with respect to u, so e to the negative as is a constant, so we can bring it outside. Now that is the Laplace transform. We've got a u there instead of a t, but u and t are just dummy variables. So if we wanted to, we could go back to this. Let's replace u with t now. So we end up with e to the negative as times f of s. All right, so that is our derivation. And in practice, the way we're going to use it is one of two ways. The Laplace transform of f of t minus a times h of t minus a. is e to the negative as times the Laplace transform of f, which is written this way. Or you could do that backwards. The inverse Laplace transform of e to the negative as times f of s is the inverse Laplace transform of f of s, but you have to replace the t's when you take this transform with t minus a. You're going to take all of that, and you're going to multiply by the Heaviside function at t minus a. And that's going to give you f of t minus a times h of t minus a. Now there's also an alternate form of this theorem, but we'll do that when I have a charged battery on my computer. So that's the end of this video. I will charge the battery, and then we'll do some examples of applying this in the next video.